10 years he was the head of theoretical department in L.D.Landau Institute, and one of his nice ability, I know him more than 40 years, he's very precise, exact. If he says that he comes at 3, he comes at 3 at the same day, because some of my friends can come on other week and not at 3 but at 5. About his hobbies, I know one, he's good downhill skier, and so some years we met in very nice place Bakuriani, now in Georgia. So I'm not sure that he played on some instruments, but maybe you could. So the title you see, so it's real talk about the topic which we announced in our program, membranes.
Very good.
Okay, thank you, Misha, for presentation. Thank you all organizers for inviting me. And many thanks to all of you for coming to my seminar instead of doing something else, perhaps more interesting or useful. The key words in my title, pores and membranes. And I will be happy if I would be able to say what are these guys, membranes and pores, and what for they are interested in. We are interested in these guys. Membranes. Membranes are everywhere. In biology, I would say that in human body, the total surface of all membranes is 200 kilometers square. It's a typical size of new Russian oligarch secondary residence, dacha. So each of us, 200 square kilometers. Membranes are equally widely useful and widely utilized in various industrial processes, including food preparation. And as well, membranes inform objects quite useful in many applications in astrophysics or gravitations. And just in contrast to famous Landau statement that astronomy will never be as important as gastronomy. From the membrane point of view, gastronomy and astronomy are equally important. Membranes also quite attractive for mathematics. That's why our program here. Because membranes are self-organized, constructed from building block which calls amphiphilic molecules. These molecules have two different parts, polar heads like this and hydrocarbon chains. And due to this frustrating feature, because polar heads love water because they could reduce electrostatic energy exposing to water, and hydrocarbon tails chains, they hate water. So they self-organize forming such objects. Typical thickness, its molecular length, it's 40, 30 angstroms. And lateral size could be as large as several millimeters. So mathematically, with very good accuracy, just two-dimensional surfaces. And if
you put the same thing into oil or petrol, would they?
Yeah, sometimes it could reverse organization. Yes, absolutely. But again, it's with very good accuracy, 10 to minus 6, it could be considered as two-dimensional surfaces. So it could be considered as physical realization for mathematical surfaces, and we could study or illustrate some mathematical properties just using appropriate construction from membranes. And vice versa, we could study some physical property applying some mathematical knowledge to this. Partially, it's motivation for my talk to attract your attention, much more educated people here in the audience, to this problem, which could be useful for application of your skill. So it's about membranes. Membranes performing amazingly sophisticated functions, many amazingly sophisticated functions, but there are two principal functions or say operations they have to do. first, it's a building block or construction block for cells. So they should protect cell inside of the cell from environment. They should be quite stable to do this. From other side, from time to time, membranes should allow some communication outside environment and inside, just to transfer some ions or molecular complexes or some medicamentation from outside to inside. How to combine this seemingly contradictory functions? The same as we are doing in everyday life. In our houses or flats, it depends on our level. Just opening for dynamically, so to speak, opening windows to exchange air inside and outside. And membranes, they are doing the same thing. They open from time to time pores, just to allow this exchange of material inside and outside, and close them, keeping stability and possibility for permeation. So intrinsically, all interesting properties of membranes are dynamical. Static or thermodynamic matter, in fact, it's dead matter. Living matter must be dynamical. It's one, say, philosophical motivation for my talk, and other motivation is a bit more practical. Recently, very intelligent methods to study pore formation and dynamics of membrane has been developed. It's called very scientifically DTS, dynamical tension spectroscopy. It's useful to have scientific title for the method, to apply for grants, for publications, but in fact it's very well known in everyday life. It's aspiration by pipette materials. But in spite of these deceptively simple methods, it's very useful, and it leads to very important information about material properties of membranes and dynamics. So how...
is it millimeter or?
Yeah, it's the size it's about millimeter, 20 millimeter it's here, yeah. So with very good accuracy and thickness, it's okay. Mm-hmm.
What is that we are seeing here?
You see in the surface of membrane, here it's pipette, and we could study, I will show what we could study.
Spherical.
It's almost spherical, yeah, but because...
How big the membrane is? If this is 2 centimeters.
Like this, yeah.
It's a sphere of 2 centimeters diameter.
Yeah,
2 centimeters.
yeah, yeah.
So why micro?
Okay, it could be used not only, it's not necessary micro pipette. For this, we could use conventional pipette from pharmacy.
Yeah.
But this is artificial membranes. It's called giant vesicles. But it could be used for much smaller objects. The same methodology. So it's about these techniques. So what is input and output this technique? Input, it's, as I told, pipette and, say, photocamera. And output, we could measure these two distribution functions. One distribution function, it's critical stress, when membrane will be eventually destroyed by this tension. And this quantity very important for to extract many material parameters. And second output, it could be found lifetime or rate of the breaking for the membrane. Again, it's quite important parameters. Concerning the first critical tension for membrane breaking, naively, we could estimate that to break, because it's organized like this, self-aggregating, we could break the membrane if we apply tension of the order or energy of the order of cohesion energy, the energy which put it together, amphiphilic molecules, to form the membranes. But it's very big energy. In fact, experimentally, and as you will see theoretically, it's much smaller than this. Because first, it's a dynamical process. It's not statical process. It's not thermodynamic, it's dynamic. And second, membranes are in fact quite soft materials. That's why physical property of membrane study in soft matter physics. It means that characteristic energy of the order of thermal energy, a bit bigger, but not too much. Yes?
I think maybe the reason is that to open it, you need only linear opening.
Yeah, but
Opening like this.
yeah, of course. But linear, the energy of linear opening is again, we have some mismatching along the edge. I will show you. It's statically, thermodynamically, it's much bigger than it turns out in dynamical measurements, because we are speaking about dynamics, and second, thermal fluctuations are important here. That's why it's we are talking about stochastic processes, not about thermodynamics. So this is the aim of this work, to develop theoretical approach how to describe this formation of the pores in its life, how it grows or shrinking, and to compare with experimental data. So, very naive approach. I am guided by prejudice that simple questions should be answered first. In principle, we could do much more sophisticated for general shape of the perimeter of the pores, but it's not necessary for, say, estimation. So what energy should be added to membrane if we open a pore? Clearly, there are two energies. First, as you mentioned, it's just linear tension around linear energy around the pore perimeter, pore edges. And second, because we remove something, we have some gain of the surface energy.
Are you sure that you remove something? If you cut and just go, nothing was removed.
No. We have not the same area. We lose some area just if we separate. Pores, it's pore. It's just a true.
But not a single molecule was removed.
No, not a single molecule. Mainly, I will speak about phenomenological approach. No single molecule, because it's everything what I'm talking about. It's at the scale of, say, 10 nanometers, not single molecular level. So we have two energy contribution. Clear, such potential has no minimum at all. So we should minimize. There is maximum, there is barrier, which achieve at this size. And so there are two very trivial scenarios. If initial pore size is smaller than this A, the pore will shrink. If this size is larger than this A, the pore will grow ad infinitum, and it destroys the membrane eventually. So it's trivial, but we are speaking about DTS measurements. In this case, the sigma is not a constant. Due to this pipette, the sigma changes in time. And therefore, even if initially the pore size is smaller than A, in time this A decreases, because A is inversely proportional to sigma, decrease, and eventually it becomes smaller than, it becomes larger than A in time. And so eventually the membrane will be destroyed. And because we are speaking about dynamics first, and second, we are speaking about system with at finite temperature, with quite soft energetical parameters, we have to take into account fluctuations. We are speaking about two stochastic, two dynamical processes with fluctuations. Small digression, yes. Our workshop, before to continue this stuff with, because before to continue this stuff with this two stochastic process, I would like to make small branching digression, because our program about topology and what I'm talking about, this specific paper, specific work, has nothing to do with topology. I know next to nothing about topology, besides few jokes like definition that topologist is a person who is not able to distinguish between coffee cup and bagel. I can, so I'm not topologist, but the objects I'm talking about, membranes and pore, intrinsically topological objects. And so I'm not topologist, what I'm talking is not topology, but objects are topological. And to illustrate this, I may spend some time, few slides, to explain what I had in mind. So one can introduce, I told already, membranes are formed by amphiphilic molecules with two parts, polar heads and hydrocarbon chains. And what is shown here, it's very happy world. So everything is happy, everything is consistent. The area here, no any constraint, and area inside. And to describe this measure of frustration between polar heads and tails, one could introduce this steric packing parameter. Nominate its volume of the chains, average volume of the chains, and denominate its average volume per one polar head. L is membrane thickness.
In biological membranes, usually you have also some material in between.
Yes, absolutely, in between. Okay, in you are right in two senses. In biological systems, it's very seldom we have membranes without proteins. But proteins could be either on the surface or just.
They're inside.
Yeah. Inside here, there is inside hydrocarbon chains. But the difference with real biology, of course, enormous. In real biology, biological membranes, they are constructed from 400 different species. And I'm considering, again, guided by prejudice, that simple questions should be answered first. Next step, we will discuss what happens, not in this seminar, don't worry, what happens if we have some mixture of lipids here, if we have some external objects. It could be discussed, it's not something, yeah. So, if this parameter 1, as it's shown here, everything is fine, and we could form flat planar membranes. If we have infinite number of molecules, we would have infinite size. Everything is fine. However, if this guy is smaller than unity, they are not happy. There is frustration. And to relieve this frustration, there are two options. The same if it's bigger than unity. To relieve, there are two options. Either produce some curvature or just produce pores. It depending on material parameters, either curvature or pores could be more or less advantage. So if nu is smaller than unity, unavoidably some kind of frustration appears and something should be done, either to curve or to produce pores. I consider, just for illustration, such a situation when to curve we have to pay more energy. For example, this membrane attached to a substrate. So to curve we have to pay enormous energies. I consider the case when more easy to open a pore. I told already that membranes are self-aggregating. What does it mean, self-aggregating? It means that they love to aggregate. It means that the number of molecules forming the membrane, in equilibrium is precisely to satisfy equilibrium condition. Thermodynamical potential or free energy over number of molecules forming the membrane should be zero. It's equilibrium conditions. And if in the main approximation the area per one molecule is some constant, it means that this derivative over area is also zero because they are proportional. It means that self-aggregating means that surface tension in main approximation very small or zero. And so to write the energy of the membrane, we have go further in expansion over the parameters of the surface. We have to expand to include some curvature terms. This is the energy of membrane. So the contribution proportional to area, to surface, is absent due to these conditions that surface tension is anomalously small. And then there are two terms related to curvature. And there are only two invariants in the main approximation. Mean curvature, square here, both quadratic over the curvature, and Gaussian curvature. So why I told that pore are intrinsically topological? Because, as you know better than me, there is Gauss-Bonnet theorem, and this guy integral over Gaussian curvature. It's just topological constant, genus of this surface. But if we have a pore on the surface, we have to subtract the integral over the perimeter, solid angle over the perimeter. So this guy depends intrinsically on topology, on existence of pores. What I said, this trivial, almost semantic arguments about frustration and how to relieve creating curvature of pores could be formulated a bit more, say, scientifically in terms of what does it mean that we have a pores? We have some. It means that we have to produce some rearrangement of these molecules. And naturally, we could introduce some vector field associated with these molecules, because molecules basically vector objects. There is polar head and there is hydrocarbon chains, quite straight.
Excuse me, if you make a pore, this means the rearrangement of molecules. This means that the total area of the membrane does not change.
Okay, I consider it does change because we have open pore. It does change. Why?
I mean, the total.
We have a rearrangement not in order to keep the total area constant. We must have it just to reduce a little bit, because to expose this guy to water, we should pay enormous energy. Try a little bit curve or open a pore just to avoid this huge mismatching energy.
Could I ask your I missed it. C1 and C2 are.
It's sorry.
Are they the curvatures?
Yeah. So if we have any curvature, we have two principal radius of curvature.
So
C1
that's the mean curvature then.
Yes. Excuse me. Yeah. So to describe pores, to describe this misalignment of amphiphilic molecules, we have to frame membrane with this vector field, which describe how molecules happy or unhappy with curvature and pore formation. Just for normalization, for convenience, it could be put the modulus equal 1, and I choose the third component of this vector equal this packing parameter I've introduced before. And so if we have some vector field, non-uniform distribution, we must add some energy related to this non-uniform, gradient energy related to this non-uniform distribution. I'm pure phenomenologist, no any microscopic physics, it's just phenomenological arguments. So K is a known parameter of the order of energy to pay for this curvature. It's first non-zero terms. And besides the term you mentioned related to linear tension about these pores. We have to minimize this, and we know that the non-trivial minima of this energy, it's so-called instantons. So we have to find the energy of this instanton, but unlike conventional instanton, which,
May I ask you the former?
yes.
What is this partial derivative I of the vector field to square? Yeah, here. It's not rotational or something?
No, it's fine. It's okay. It's symbolic, of course. Yeah. Okay, we have to write appropriate combination. It's only to say that it's gradient square, but of course you should write rotational invariant combination. Yeah, of course. Yeah, it's. Thank you.
What is Q?
Q is some formal vector describing misorientation of molecules, and to describe pores, the minimal ingredient should be added to this curvature energy. The minimal ingredient is just some vector field. So it's formal field describing how locally these guys try to avoid to pay too much energy for curvature and for pore formation.
Can you fix it? What does mean delta EQ in square? What does mean mathematically? What does mean?
Say again.
What does mean? What does
it
so?
mean?
What does mean?
Okay.
It's
Let me.
QIJ.
Yeah. Okay. It could be different term. For example, it could be div q square
Oh yes.
with certain coefficient. It could be q times curl q. As I told, it's a bit symbolic. So all combinations.
Yes, but you fixed this. Yes.
Yeah.
Okay.
In the third one, it's just scalar product. Twist.
But
You need to.
you say that it could be, but what is it?
Yeah, that's
Okay, it's phenomenal. All of those guys.
combination.
Yeah, but in the case all constant here are the same. In the case all constant here is the same. It reduced to the following very trivial things: di qj square. That's it. Or when I put down minimization Euler-Lagrange equation, it reduced to Laplacian q equals 0 I have to solve.
Q is restricted to the surface, or it's in the neighborhood of the surface, or how do you figure it?
It's,
On the line.
yeah.
It's defined-
Q is defined on the surface, but non-trivial contribution comes from the line.
I see. To have an entire.
Don't you need two curves? I mean, you need two derivatives, so it's Q.
Yeah, it's square, it's to the, yeah.
No, I'm talking about the line above that. This one. No, below that. Yeah, curl Q. You need
Square.
curls.
Square.
No.
Curve.
One.
One.
Everything is fine, yeah. It's quadratic over gradient. It's minimal first non-zero contribution.
No, it's
If needed, I could.
cube. You cannot have cube.
It's defined on the surface, so it's defined on a two-dimensional manifold.
Yes. Nabla here is derivative over two dimensions.
Unless
But you have Q to the power 4 now. Or am I wrong?
No.
Q dot
It's
Q.
Q. It's Q.
Yeah. This term over Q is fourth order, but over gradients it's. So if, as I told, all coefficients here are equal, it's Q modulus of Q is 1. I define it's normalization.
Okay.
Okay? May I continue? Good. So non-trivial minima of this symbolic energy is instanton, but unlike classical, something wrong?
No, it's curl Q to square, but not Q curl Q.
No, both terms could be added, but don't forget that Q is unit vector. Q square is 1.
Not discuss this.
Okay.
I could write the same in earlier angles. There are different forms. Don't pay much attention. It's symbolic. So I have to minimize this energy, this action.
Does that symbolic expression includes coupling between field Q and geometry or not?
Yes, because not here.
No, that's the term I'm asking about, because you include the mean curvature and regular curvature. So how about
No. There is good questions. There are not only these terms. So in this approximation, indeed, it's totally decoupled. Because what I said at the beginning, I consider the situation when to relieve frustration, the best way to relieve frustration, it's pore formation, not curvature. But if I like to take into account the second way to relieve frustration, I have to couple both. It could be done, yes. So as I told, it's instanton, but unlike conventional instanton, we have to map plane without pore. So it's written somewhere here to semisphere, so it's half of the instanton. Next, it's conventional mathematical procedure. I'm using stereographic coordinates. R capital is the size of the instanton. I'm calculating integral. I'm minimizing.
Wait.
Uh-huh.
Just you see. Go on.
Thank you. No. So I'm minimizing, and I found that indeed, after simple procedure, there are a range of parameters where this way to relieve frustration, just forming the pore, is more advantage than to create curvature. So I am perfectly right, neglecting coupling to curvature. So this is pure static, pure thermodynamics. So it's almost has nothing to do with what I said before, but it's just to illustrate that pores are intrinsically topological objects. There are topologies, there are instantons, there are everything here. So let me come back to the mainstream of my talk concerning the dynamics. So what I am considering, the pore is formed by fluctuations, and then it grows, and there is an external loading. I'm speaking about this DTS, dynamical tension spectroscopy experiment. So there is pipette, this guy, the potential where the pore leaves depends on time, and I have to solve this Langevin-like equation. So V is this potential, but don't forget this guy is dynamical, and F is random noise, it's fluctuation, thermal fluctuation, Gaussian random noise.
Why is the potential time in the potential?
Because we have, I'm considering situation with DTS device, dynamical tension spectroscopy. When there is applied, when we are using pipette to study this pore formation and dynamics. Because
time-dependent suction.
Yes. Because my aim to describe experiments at the end of physics, basically experimental science, I have to describe. I'm paying for this. So you will see at the end that indeed such a simple, almost trivial approach describes quite reasonably experimental data. And besides, as a byproduct, some important material parameters can be extracted from this. For example, internal viscosity, because viscosity due to so-called fluctuation dissipation theorem enters this random noise. I could extract not only tension, not only lifetime, but also some dynamical kinetic characteristic of the membrane from this data. So it's convenient to transform everything to dimensionless variables. During Soviet time working on atomic bomb projects, for some people not so reliable or suspicious, they were allowed only to see dimensionless equations. So it's not motivation for me to show you these dimensionless equations. Another motivation I have in mind that it allows to write down equations in more intelligent and compact form. So don't pay much attention to this definition. The main parameter, this guy, it's controlling parameter of DTS experiment. It's applied force, applied sucking aspiration tension. And there are two limits for this Langevin equations. One is when this guy is smaller than 1, dimensionless guy. In this case, it's diffusion. And another limit when it's larger than 1, it corresponds to drift. It's mainly driven by pipette. To the same point, so now it's dimensionless equations. I can show to even capitalistic environment. No secret. So I have to solve this. In principle, it's possible to solve directly, just to solve. It's trivial equations. But the problem is that it can be solved for given realization of noise. And then I have to average over noise. And this, in practical terms, almost undoable. So instead of solving this, I am replacing these equations by so-called Fokker-Planck, or in this business it's often called Smoluchowski equations for probability density. Here it's just to illustrate how it looks like the potential. Look, it's the potential in this dimensionless units.
What is surface tension timescale?
Characteristic timescale, I show it could be an experiment in real life, you mean? I show you.
What does it mean?
It means that I apply this pipette, I could change it. Look, I could change it at such a rate. Loading rate could be changed 4 order of magnitude from this guy to this guy, millinewton per meter per second. So characteristic time to scale to change it from this interval. It was your question.
10 to the 4.
Yeah. So it depends. It could be quite different indeed. So now I have to solve these equations. As I told, it's not very convenient to solve directly. It's convenient to transform this equation into Fokker-Planck equation for the probability density and to solve these Fokker-Planck equations. It could be done very easily if there is no pipette at all. So in static case, just in this case, in dimensionless units, we have no distribution at all for critical stress, for critical tension, and the solution of Fokker-Planck equation is trivial. It's shown here. So if no external stress in dimensionless units, if V controlling parameter is 0, in this case the solution is trivial. It's shown here. It's known it can be done easily. But if it's not the case, if dynamics, it's just formal presentation. If dynamics is important, if this potential depends on time, the solution is much more tricky. And to solve this, let me skip few slides. So what I have to solve? I have to solve the Fokker-Planck or Smoluchowski equation for density probability. What density probability? Density probability to have given size at given pore size at given time at given tension. I have to solve these equations. And then after that I have to find all what I am interested in, namely lifetime for the membrane and critical tension to compare with experimental data. But lifetime, to find lifetime, in fact, I need not know this full probability density. I need to know, it's called in this business, it's called first passage time. I need to know only first time the membrane, the pore, cross the barrier. Because if it cross, that's it. The game is over. Membrane will be destroyed. So I have to calculate not the full probability density, but only first passage time. Philosophy behind first passage time quite known in sport business. It's called seed law. To gain a series of games, you must game at least first game. So it's first passage time philosophy. So I need not know this guy, P. I have to know only first passage time. But to formulate equations for this first passage time. It's very non-trivial problem. I was not able to formulate it myself, but luckily for us, great Soviet mathematician von Triagin he was formulated the equations directly for this survival probability of first passage time. It was published in Pure Physical Journal in 1933, and now it's widely cited paper. So it's extremely useful in this business. So I have to solve these equations. This is adjoint Smoluchowski operator. It was shown in previous slide, but don't pay much attention to this, how it looks like. So this is doable. Unfortunately, analytically, it can be done only in the case when everything depends only on one coordinates, one time and one coordinates. But it's precisely what I need for circular pores, because everything is radially symmetric.
I think we should see that operator.
Good.
Zero, if you don't mind.
It's my pleasure. So, here it is.
All right. Okay. Yeah.
So, after some quite involved, but in fact straightforward algebra, I could find the results, and results can be formulated in terms of green function for that equations, but for infinite system. What is the advantage of this Pontryagin method? One more slides let's skip. So this is the equations I am solving. This is change of variables. This is formulation of the Pontryagin equations in my coordinates. This is change of variables. A little bit more. In green function, I could expand this guy over eigenfunction of certain Hamiltonian. This Hamiltonian, again, one more change of variables could be transformed, it's formal Hamiltonian, could be transformed in quite civilized form, just harmonic oscillator. And the only non-trivial, after all this transformation, the only non-trivial issue here that this guy, this harmonic oscillator, I have to solve this Schrödinger-like equations, but for non-usual boundary conditions.
Well, C, of course.
Yeah, sorry. I have to solve this for non-trivial boundary condition. It's reflecting boundary condition at z equals 0 and absorbing boundary condition at z equals a. But it's doable. And formal solution written here, it's parabolic cylinder or Weber function here. This constant should be found from normalization and boundary conditions.
So we look for real functions.
Yes. No. It should be combination must be real function. Yes. Yeah, but it's non-trivial harmonic oscillator with non-trivial boundary conditions. Yes. But functions are the same. And this is formal answer. Unfortunately, it's exact, it's analytical, but formal, it's useless for practical application. Anyway, we have to use Mathematica to put it to compare to something. We did it. And here is results. So it's distribution of rupture tension, depending on parameters describing pore formations. And what is shown here is our calculations, and envelope, it's experimental data. It's fantastic. It's unbelievably good. With two fitting parameters, I have to admit.
Which eigenvalue do you choose? The lowest?
Lowest, yes. It corresponds just breaking, yes. Here this shown DTS spectrum. Again, how it depends on parameters of the model. Again, here it's inverse. Points are experimental data, and line it's our calculations for different loading rate. unbelievably good agreement, I'm ashamed. Okay, it's the same. So in fact, it's the end of my talk, and the last slide and the last message you may take with you at home. It's shown here. My message is that membranes are also inexhaustible. This very hard. It's for Russian people of my generation and even much younger. We have to pass a number of examinations about this book. It's hardly readable. Mr. Lenin in this book, he fought with his enemies. It's impossible to read, but nevertheless we have to pass many examinations. And one sentence from this book we remember by heart, all of Russian of my generation. It's written here: the electron is as inexhaustible as the atom. So I am using generalization of Lenin's statement that membranes are also inexhaustible.
This looks like a very recent new edition.
This book? Yeah. It's always, yeah.
It's just never been read.
Thank you very much.
What is the significance? The electron is as inexhaustible as the...
I don't know whether he proposed himself, Lenin, this sentence, or he found somewhere. This I don't know. But this known for all Russians of my generation.
He learned this more than 20 years, starting from the childhood till university. We learned what it means.
Yeah.
You probably need another 1,000 years to understand it.
Can you say?
But it's hardly readable book, indeed. It's.
But certainly, we learned it. Yes.
So first of all, so the talk is soon we
Thank you.
question and comments.
Comment, complaints.
I didn't know that Lenin was a material scientist, but I guess this is evidence that was.
And not only high energy scientist, mathematician, up to you to choose.
General sentences, they have sometimes additional meaning, which in
Yeah,
the
yeah.
moment you don't know what it, but
It's
sometimes it's
metaphor.
very deep. It looks, if you say that the equation has
So actually, I have a serious question.
the root is general, but if you say that the root of this concrete equation is so and so, it's simple.
So now actually I have a serious question.
You have
So-
questions?
Yeah, serious one. So the pores themselves presumably have dynamical behavior on
Right.
that rate. So that's what I was trying to get some sense of, whether they have, attractive behavior, repulsive behavior, quadrupolar behavior. Just, any comment on that?
Okay, right here in this talk, in this work, I consider one single pore. So attraction, repulsion is not relevant. But it has been done, partially by myself as well, how this manifold of pores could behave. And there are very non-trivial features because there are different kind of attractions. There are attractions due to elasticity of the membrane. It's long-range attraction. It produces some pore structure. So it's very, very rich physics behind. As I told at the beginning, my aim just to attract your attention that there are interesting objects where smart, mathematically educated persons could apply their skills. I'm not.
You had that miraculous agreement between theory and...
Yeah, but I should admit two fitting parameters. So it's,
Well, that's what I was going
yeah,
to
yeah, yeah.
ask.
It's two fitting.
Only two.
Only two, yeah.
There seem to be
Okay.
freedom there, even more than two.
No. Only two parameters apart from
Three energies.
Okay.
The ratios of...
Yeah, but I need only ratio of the energy, and besides, of course, I fix the general level, so it could be, yeah. Behavior is with two parameters, but absolute value 3.
Yes.
In the soap bubbles, which are the closest to what you described with two molecular layers, somehow I don't see how you can open a pore without destroying it.
Yeah, it's quite different, unfortunately. It looks like the same business, the same physics, but for soap bubbles, the main contribution is surface tension.
Yeah.
In our case, the main contribution is curvature, pores, not surface tension. Yeah, not
No,
surface
there is also
tension. Surface tension,
curvature in soap.
of course, yeah, but main contribution is surface tension. Yeah.
Phenomenon
Okay, it's
smaller or higher.
It's like, again, coming back to Mr. Lenin and Marx and all this stuff, it's like we learn at school or at the university, it's Hegel law, transformation of quantity into quality. Here, the surface tension is so small that could be neglected. It's another quality. But basically, you're right, it's similar physics, but not the same range of parameters and behavior quite different. Yeah.
The parameters are different.
I have a question, maybe just a silly question. The Hamiltonian for the Q field, it just looks like nonlinear sigma.
Absolutely, absolutely. That's why you are right. Yeah.
Yes,
Here it appears as a pure phenomenological approach. So I consider if there is some variation in space of this vector, we have to pay energy. But Hamiltonian, indeed, it's the same. That's why instantons appears.
Yeah. So do you need to just introduce the WZW term, let's to written term?
Okay. If for what I told, I need not this. But if some more tricky problem, because what I told, the only things in this business that there is condition when, in spite of this additional energy, the pore could be open because it's energetically, for certain value of packing parameter, it's energetically favorable to form a pore instead of have this frustration, to relieve this frustration. But for more sophisticated or more different problem, it could be indeed, should be added this term to this nonlinear sigma model.
Maybe just for your case, you have boundary conditions. So.
Okay, might be this is the matter. But the matter, okay, in my case, just it depends what questions I'm asking. Here I ask the only questions whether it's possible to form a pore. And this business show me that there is range of parameter where it's possible. But if I'd like to describe more details, you're right.
If there's no questions, so thanks. Thank you.